In this presentation, I'm going to be talking about estimating the health impacts of air pollution using satellite-derived concentration estimates. Satellite data allows us to estimate the concentrations of air pollutants at ground levels at increasingly higher resolutions. These high-resolution pollution estimates can then be used to identify neighborhoods within cities that may experience high rates of disease and mortality associated with air pollution exposure. This study aims to estimate the health impacts of air pollution at the city and neighborhood level using Oakland, California, within the Bay Area as a case study. Until recently, many air pollution health impact estimates have been reported at the global, country, or county scale, which can mask potential spatial heterogeneity at finer spatial resolutions. No best practices exist for quantifying air pollution health impacts at the local level. In our study, we explore how varying the spatial resolution and source of pollution levels and disease rates can influence estimates of air pollution health impacts at the neighborhood scale. We believe this analysis. In order to calculate the health burden of air pollution, we use health impact functions derived from epidemiology studies which link air pollution levels to incidence of certain health outcomes among populations. The attributable fraction of a disease can be described as the amount of disease in a population that is the result of a risk factor or exposure, in this case air pollution. For our examples in this presentation, we are going to focus on deaths attributable to air pollution, though we also looked at other health outcomes such as cardiovascular mortality, asthma emergency room visits, and new cases of asthma. From epidemiological studies looking at the relationship between air pollution and health outcomes, we were able to derive a risk estimate that quantifies the amount of disease we would expect for each unit increase. In order to apply our epidemiological risk estimates spatially, several other data inputs are needed. We also need the spatial distribution and number of people in our population of interest. And we also need to know the rate at which the disease occurs in the population, as well as its spatial distribution. And then finally, we need the spatial distribution of our pollutant concentrations. In this study, we obtained air pollutant concentrations from three sources: fine particulate matter from a satellite-derived model, and nitrogen dioxide from both a land use regression model that incorporated satellite tropospheric column nitrogen oxides, as well as nitrogen dioxide measurements from monitors onboard Google Street View mapping cars. The result of the calculation is the number of cases of disease in the population that can be attributed to. Long-term exposure to fine particulate matter is strongly associated with increased risk of mortality, contributing to a large burden of death and disability in the U.S. and globally. For our fine particulate matter dataset, we used input concentrations from a satellite-derived model. This dataset is a hybrid model that produced daily estimates of fine particulate matter. This neural network trained hybrid model incorporated aerosol optical depth, AOD, from the Moderate Resolution Imaging Spectroradiometer, or MODIS, on the Earth Observing System satellite, as well as central site monitoring data, a chemical transport model, and numerous other meteorological and land use variables. This graph shows the daily maximum concentrations in the Bay Area, showing that they regularly exceed the U.S. Environmental Protection Agency. Nitrogen dioxide is a traffic-related air pollutant, exposure to which has been associated with the development of asthma and increased mortality. We compared two NO2 concentration estimates to explore the influence of different exposure assessment techniques on our estimated health impacts. Our first nitrogen dioxide concentration dataset is from a land use regression model. Land use regression models use land characteristics and other input variables to estimate concentrations where we do not have measured concentration data. This model incorporated tropospheric column estimates of nitrogen oxides using data from the SCAMACHI instrument aboard the GOMI-2 satellite. The satellite column concentration. To compare the results received from the land use regression concentrations of NO2, we used measured data of NO2 concentrations from an innovative mobile monitoring dataset. Between May 2015 and May 2016, Google Street View cars took repeated 30-meter road segment measurements in neighborhoods throughout the Bay Area. This created a dataset of over 3 million Google Street View measurements in the Oakland area, which was then used to create an annual average dataset. The Google Street View dataset shows high concentrations at and near roadways, more so than is seen by the land use regression estimates. We can also see through the density plot that the land use regression model has a higher median distribution of concentration values as compared with the Google Street View values, which has a large. We found that when comparing the results calculated using the Google Street View mobile monitoring data versus the land use regression estimates, using the land use regression model resulted in a greater overall estimate of the NO2 attributable mortality as a result of the overall higher median distribution of concentration values. We found that both the Google Street View and the land use regression models identified similar spatial patterns of disease risk due to NO2. However, we found that the Google Street View concentrations resulted in more spatial heterogeneity in NO2 attributable mortality compared to the use of land use regression estimates. The Google Street View dataset appears to identify areas of disproportionate burden of disease, with several hotspots seen here. The other part of this study was to determine how estimates of air pollution attributable health impacts vary when we use more finely resolved baseline disease rates at the census block group level compared to the county level. While county level baseline disease rates are fairly easy to obtain, they lack spatial heterogeneity and may overestimate baseline disease rates in some neighborhoods and underestimate in others. We were able to obtain baseline mortality rates at the census block group level. When we applied these higher spatial resolution mortality rates in our health impact function, we found different areas of elevated air pollution attributable health burden as compared to the application of county rates. As we can see here, the census block group baseline disease rates yielded results with a higher median distribution, as can be seen in the box plots, as well as greater spatial variation, as can be seen in the maps. We conclude that in this presentation, we've seen the ability for highly resolved spatial data to help public health researchers identify spatial patterns in the health burden attributable to air pollution within cities. The data sources we explored were satellite-derived pollutant concentrations, innovative mobile monitoring, and highly resolved baseline disease rates. We've demonstrated that the baseline disease rates influence spatial patterns and risk, making it important to obtain accurate estimates of disease rates for each neighborhood and not just at the county level. In a spring 2019 meeting at the George Washington University, representatives from local and state governments emphasized the need for this type of highly localized risk estimates in order to help inform local air pollution policies. It is the hope of this study that local health risk assessments will become a way to identify disparities in risk and help inform local policymaking in cities worldwide.